Hello students, we're going to talk this morning about how the two different sorts of atoms join to form three different sorts of bonds. So the point of today's lesson is understand that chemical bonds are caused by electrostatic attractions that arise because of the sharing or transfer of electrons between participating atoms, and the valency is a measure of the number of bonds that an atom can form. So as we've talked already, we know that there are two sorts of elements, or two main types. There's metals and non-metals. So if you were to join a metal and a metal, you'd form a metallic bond. A metal and a non-metal would be an ionic bond, and a non-metal and a non-metal form a covalent bond. So if we're joining covalent bonds, we generally say that the electrons are shared between the atoms, and they will form molecular compounds or molecules. Now, the bonding in a metal with another metal is we say that there's a sea of electrons, and there's the positive parts of the atom. So there's positive cations in a sea of electrons. Now, we generally call that compound an alloy, for example, if we're mixing two metals together. If you join a metal with a non-metal, it's an ionic bond, and the non-metal will steal the metal's electron, and that will form a crystal lattice. So we'll have a crystal forming. So if we're looking at metallic bonds, as I said before, there's positively charged ions, and in metals they don't really hang on to their outermost electrons very well, so that forms the electron cloud, and that's a negatively charged sea of electrons. So a metallic bond is the attraction of the stationary metal cations to the surrounding delocalized electrons. They're delocalized, so they can float between the different cations. The chemical bonding that results from the attraction between a metal and cations and the surrounding sea of electrons. Now, the outer energy levels overlap and allow the outer electrons to move freely throughout the metal, and the valence electrons do not belong to any one particular atom. So metals form our simplest form of crystals as well, but you'll see that they're quite flexible as opposed to ionic crystals. So in metallic bonding, metal atoms have a weak hold on their valence electrons, and that allows the electrons to flow, so conduct electricity, for example, or heat or light. So the electron mobility accounts for the electrical conductivity and heat conductivity, malleability, that means you can hammer it into sheets, and ductility, which means you can draw it into wires. Now, metal crystals bend. That means they are malleable rather than cleave or crack, like ionic crystals, as the cations can slide past each other. Ionic crystals tend to break apart due to the repulsions between the cations and the anions. So remember, in an ionic, it's a metal and a non-metal. The non-metal will form the anion. So if we look at ionic bonds, an ionic bond results from the electrostatic attraction between two oppositely charged ions. Now, the octet rule tells us that generally it's going to have 8 electrons in the outer shell. So in forming compounds, atoms tend to take on the configuration of the nearest noble gas. And hydrogen and lithium, for example, those around helium will just form 2, otherwise it's going to be 8. The metal forms the cation, which is a positive ion, when it transfers the electron to the non-metal. So you can see that, for example, sodium, it transfers its S1 electron into chlorine's P6 orbital. So we are forming a positive ion here, that's positive, and the non-metal is negative, so that's the transfer. Now, what ends up happening is that there's this packing arrangement of positives and negatives close to each other, and that's going to make it easy to form a crack, for example, down a line like that. That's when I'm talking about cleavage. That means that cracking. Covalent bonds are when non-metals join with non-metals, so the electrons are shared, and so the non-metals have their outer shell full to have that 8 electrons, and so that's that octet rule again. As I remembered, as we mentioned before, hydrogen would be the exception to that, wasn't it? Because it's going to be acting like helium, with only having the s2 orbitals filled rather than the s2p6 orbitals done. Now, if I want to look at covalent bonding, it's when the electrons are shared. So the classic example is looking at two atoms of the same type. It's going to form a non-polar bond. So when the electronegativity, that's the ability to attract electrons, is quite similar or less than a half, and there's less than a half difference in electronegativity, you're going to form a non-polar covalent bond. But sometimes one electron is more negative than the other. So if I look, for example, at chlorine, it's much more electronegative than hydrogen, and that's going to form a polar covalent bond. And so hydrochloric acid is a good example, which is HCl, or water is another classic example. And although water is very common, it's very unique because of its polar nature. So with covalent bonding, the electrons are shared. So you can see the sharing of electrons. But with ionic bonding, there's the complete transfer of one or more of those valence electrons. And the full charges relate to those cations and anions then. When we consider the octet rule, so if we look at fluorine and the halogens, for example, the p6 orbitals will need to be shared. So what they're going to do is share the p5 to fill in the p6, and so we are sharing 7 valence electrons. If we're looking at oxygen, we're sharing what the p4 and the p5s there to fill in the next 2, and so we are sharing 6 valence electrons. With the nitrogen group, so group 17, we are 15. We're sharing 3 electrons to fill in the outer shells. And so you can see if you're sharing 1 electron each, you'll form single bonds. If you're forming 2, you can say we're forming double bonds. And if we're sharing 3, we can say that we're forming triple bonds. And so we are looking here that those in group 17 will share 1 electron each. Those in group 16 will share 2 electrons each. Those in group 15 will share 3 electrons each. Those in group 17 generally then form single covalent bonds. Those in group 16 double covalent bonds. Those in group 15 will form 3 covalent bonds. And this is often called the honk rule. So hydrogen and halogens form single covalent bonds. Oxygen, so that's group 17, so group 17. Oxygen, which is group 16, form 2 covalent bonds, or 2 singles, for example. Nitrogen, so that's group 15, will form 3 covalent bonds. Carbons and silicons can form 4 covalent bonds, and that means that they're sharing those 4 valence electrons. Finally, can you understand that chemical bonds are caused by electrostatic attractions that arise because of the sharing or the transfer of electrons between participating atoms, and that the valence is a measure of the number of bonds that an atom can form? When you've done that, can you complete your exercises to master this concept, please?